Hello friends, welcome my channels. Today's discussions is very interesting. This is the introduction to tensor and differential. Friends, it is very important topic for physics. I suggest some book name. I want to suggest some book name, that is my suggestions. My suggested book. Number 1, Differential Geometry with Application, Differential Geometry with Application, John Opria. And another important book is Theory Curves and Surfaces, Differential Geometry. This is my book name. Another is Differential Geometry of the Physics, but I don't know the author name. So friends, I think that this book is very available. This book, so you can buy it and for study. Let's start our discussions. We start. That is space of n dimensions. Space of n dimension, friends. We do not. This is the main factor that we have to learn. What is the n-dimensional space? So friends, we have learned 4-dimensional, 2-dimensional, 3-dimensional. Similarly, it is the n-dimensional. Let us consider an n-dimensional space space by Vn. Here x to the power 1, x to the power x power base 2 up to xn be any set of coordinate in the space, and x bar per L, x bar to the power 1, x bar to the power 1, x bar to the power 2, x bar to the power 3 bar per N be another set of coordinate in the same space Vn. Each of the per I will be a function of capital N other coordinate x bar whole to the power alpha, and vice versa. This means we can write x to the power I is equal to x to the power I bar 1 x bar capital, where I is equal to 1, 2, capital, and bar capital to the power I capital to the power alpha to the power alpha 1, where alpha is equal to 1 to up to n. We have x to the power I into x bar to the power 1 x bar to the power 2 x bar to the power 3 up to x bar. So by partial differentiation we get dxi equals to del x to the power I divided by del bar whole to the power 1 bar plus del x to the power I divided by del x bar whole to the power 2 d x bar and so on of del x to the power I divided by del bar whole to the power n x bar. So friends, it can be written, these equations can be written equals to summation alpha equals to 1 capital N del x to the power I divided by del x bar whole to the power alpha into d x bar whole to the power alpha. So friends, I discuss space of n dimensions very briefly. Now I want to discuss about tensor. So friends, we discuss visualizing tensors. Tensors is a matrix. Tensors as matrix and vice versa. So friends, you see that this is the matrix, this is the tensor, and this is the matrix. So tensors can be represented as matrix and vice versa. And this is the 2 cross 2. This is 2 cross 2 matrix. Can be 2 cross 2 matrix. 2 cross 2 matrix can be written this form, and this form I can write 2 cross 2 matrix, and this is the 2 cross 2 tensors. So friends, another tensor definitions. Tensors are natural and logical mathematical representation of physical laws which are invariant with respect to inertial frame of reference. So friends, we learned that it is invariant. It is invariant with respect to inertial frame reference. And it tensor used in fluid mechanics, hydrodynamics, Hilbert space, to tensor product. General relativity deals with tensors. Tensor from its birth. Easy to visualize, essential tool in many practical calculations. Essential tools in many practical calculation. This is the tensor applications, friends. And now I want to discuss that inner product. This is the two vectors, friends. Tensor is also called generalizations of vectors. This is two vectors u and v, and I can write that u is equal to u1, u2, u3, un, and v is equal to, I can write v1, v2, v3, vn. So friends, u dot v can be written u1 v1 plus u2 v2 plus u3 v3 plus up to un vn. It can be written this way, ui into vi. So friends, u sub I and v sub I, and this is the using Einstein convention. Einstein convention, geometric meaning, and this angle is alpha, and geometric meaning of scalar product u dot v equals to uv cos alpha mod of u into mod of v cos alpha, where alpha is, this is the alpha is an angle between two vectors. Now we can check that the scalar product is actually linear both, so this actually shows that we can check out that the scalar product is linear. So in both cases, the scalar product are product is linear, So friends, this is two vector and number v, and this is w, and lambda is a real number. So friends, u plus lambda w is equal to uv plus lambda u w. And now consider I draw a vector space L is a vector space G such that L cross L tends to R, and GU comma V plus lambda W is equal to G UV plus lambda G U comma W mapping G, this mapping G is also linear. Linearity means that scalar product is distributed. What is the linearity? Means that the scalar product is distributive. Now we have seen that tensor as mapping. Tensor as mapping which takes some number of vectors and outputs a number Scalar product is an example of rank 2 tensor. Scalar product is an example of rank 2 tensor, as it have two vector argument, as it have two vector argument. This particular tensor representing scalar product is the metric tensors. Now, for example, if we take rank 2 tensor E1 and E2, then U can be written, U is a vector and U belongs to L. Then U1 E1 plus U2 E2 plus plus UN En. It can be written this way, Ui Ei. So friends, this is the Einstein convention. Now the rank 2 tensor, general tensor, let we take a general tensor T Ij, which is rank 2. Then Tij equals to T Ei Eij equals to, it can be written, it is the twice ranked, so it can be written T E1 E1 T EI and T EI E2 up to T EI EN and T EJ up to E1 T EJ E1. So friends, this is the type of tensor where row is 2 and rank is 2. It can be written a lot of way, but where 2 is a row is 2 and n is column is n. Tensor can be represented. So for notes, this is the one kind of notes. Tensor can be represented as matrix. The numbers are called components of the tensor. The numbers of vector are called tensors. Generally change their components when you change the basis. Tensor can have this is the number 1, this is the number 2. Number 3, tensor can have contravariant and covariant components corresponding to the components of the tensor transforming against on which the change of basis. Number 4, the rank or degree or order of a tensor is the number of axes on component it has. On component it has. Thanks for watching, friends. I hope that I can give some introductions about the tensors and some introductions of the n-dimensional space. So friends, this is my first video. I shall create a lot of video for you very soon. The topic is differential geometries.